thanks everyone for coming, and thank you, Mathematical Institute, Alan, for inviting me. So, can Yule solve my problems? One rule of life, if you can get a pun in the title, always put it in. The subtitle of this talk is going to be a short history of puzzles with occasional Christmas references and some sparkling mathematics. In other words, I'm going to talk a little bit about puzzles, a bit about the history of puzzles. We're going to do some puzzles, and I might mention Christmas a few times. There's a Christmas lecture. Now, it's fantastic for me to be here because it is a return to my alma mater, where mater, the crucial word, because I was actually born on this site when it used to be the Radcliffe Infirmary. This is where I was actually born. So it's quite nice to think that, in fact, my wife might say that I was actually born in a mathematical institute, but it's quite nice that the place that I was turned into one. Also, it's true, I studied mathematics here. It wasn't maths and physics, it was maths and philosophy. And rather wonderfully, my old philosophy of maths professor is in the audience, so the pressure is on. It's true, I did a lot of maths when I was at Oxford 30 odd years ago. I also did lots of journalism. I probably did more journalism than I did maths, and I was editor of Charwell, the university newspaper. And in the last 10 years, I have combined essentially my two passions. Football's not really a passion. It's writing and mathematics. It's two serious passions in basically what I've tried to do. My first book was Alex's Adventures in Numberland, where I went around the world interviewing people as if I was a kind of foreign correspondent in the world of mathematics, interviewing people in the world of maths and sort of explaining what they did, mathematical concepts, to the general reader. That led to the next one, Alex Through the Looking Glass. Then I wrote with a wonderful mathematician, mathematical artist, Edmund Harris, two maths colouring books. And I just wanted to mention these because even though they are colouring books, you can look at them and you can colour them in, essentially they're colouring books because bookshops have a table for colouring books. Really what they are a gallery of wonderful images from all areas of maths, and even though they look the most kind of junior, so to speak, of all the things that I've done, they probably cover the widest and deepest mathematics. So 2-3 years ago, I started to write a puzzle column in The Guardian, and yes, it is a lot of pressure to try and find a good puzzle every 2 weeks. So if anyone here has any puzzles that they've just invented and they want to throw them my way, please come and see me. And this has resulted in two puzzle books, Can You Solve My Problems and Puzzle Ninja. So Puzzle Ninja, which is not really Christmassy, even though it's just out in time for Christmas. It's about Japan. I went to Japan at the beginning of the year because the puzzle culture in Japan is unlike anywhere in the world. And I found 200 or so handcrafted puzzles, and we presented it in this beautiful kind of Japanese style book, which is like lovely to hold. And I promise you, some bloke you might have heard of, very, very wise man, Marcus de Sautoy, called this book addictive, and that's an understatement. You will start doing this book and the time disappears, which that's one of the great joys of doing a puzzle, is that once you get into it, the world disappears, and there are whatever distraction there is, you can focus. And it's actually such a kind of, well, I find it a relaxing thing to do puzzles because all those distractions disappear. Now, I'm going to start off with a puzzle, which is the puzzle on the cover of my book, which, for the purposes of this talk, I'm calling Santa's belt buckle puzzle. Santa has laid out 5 shapes, which could be his buckle on his belt, and it's an odd one out puzzle. So one of these shapes is the odd one out. I'm going to give you a few seconds just to think about it. Then we're going to try and solve it together. So we'll solve it together. I'm on this side, so we'll start with this one here. Put your hands up if you think the odd one out is the only small one. One person. Hands up if you think the odd one out is the only blue one. A couple, like 3 people. Hands up if you think the odd one out is the only circle. And hands up if you think the odd one out is the only one with no border. everyone who has put their hands up so far, just listen. I'm going to repeat what I have just said. This is the only small one, the only blue one, the only circle, the only one with no border. What is unique about this one here? Nothing. It's not only anything. There's nothing. It shares every characteristic, every feature, every property it shares with another one. In other words, the odd one out is the one which is not an odd one out. So, in fact, as well as a puzzle, this is actually a subversive meta-puzzle that can a kind of subtle campaign against odd one out puzzles by kind of ridiculing them. And in fact, that was the reason why it was invented by a Russian-American puzzle expert, Tanya Hovanova, who doesn't like odd one out puzzles and wanted to use this to show why. Now, I like this because a good puzzle is also a good story. You take it, it has a beginning, you set the problem, then you work it out, you kind of there's a path that you need to go, there might be some false turns, then you have the kind of the insight, and then things are neatly tied up at the end. So I think that another reason why I like this puzzle is that it takes us on a journey. It's just that the journey at the end is also really like a joke. Now, I feel I should mention something about Christmas now because it's been about 3 minutes and I haven't, and this is a Christmas lecture. So I want to go back in time to Christmas Day, the year 800. And if I was in the History Institute, everyone would know exactly what important event happened on Christmas Day 800. Thankfully, I'm in the Maths Institute. It was when Charlemagne was crowned, was made emperor of Rome, and he was king of the Franks, but he was in Rome, and the Romans made him king of the Roman Empire, the Holy Roman Empire, so he became empire of pretty much all of Western Europe. And Charlemagne is interesting, not just because for his sort of political aspect, but because he was the head of an intellectual resurgence towards the end of the Middle Ages in Europe, and his mentor, his educator, his teacher is probably the most important early figure in the history of puzzles. And this person was Alcuin of York. So Alcuin of York, from York, ended up working for Charlemagne, starting well, he was teacher at the Palace School in Aachen, where Charlemagne lived, and he also set up a kind of network of European seminaries. He also joined up writing, did lots of amazing things. And in 799, he wrote a letter to Charlemagne in which he says, I enclose some arithmetical curiosities to amuse you. The arithmetical curiosities were only discovered about 100 years later and attributed to Alcuin. The propositiones, and thanks I'm not in the Classics Institute because you do me for my pronunciation of Latin, the propositiones ad acquendos jovenes, the problems to sharpen the young, which is really the beginning of puzzle culture. So the propositiones is also interesting. It's the first piece, the first text we have written in Latin with original mathematical ideas. So even though it's towards the end of the Roman era, if not really beyond it, and all through the Roman era, they didn't come up with new mathematical ideas. Obviously, they did maths to do all their engineering, but not in the way, coming up with new ideas the way that the Greeks did. So what were in this document? There are about 60 puzzles, several totally new types of puzzle, and the most famous one is probably the most famous riddle of all time, and it's the one where you have a traveller who is travelling with a wolf, a goat, and a bunch of cabbages. He gets to a river, he needs to cross the river, and he has at his disposal a boat, and he can only take one item at a time. He can't leave the wolf with the goat, because wolves eat goats, nor the goat with the cabbages, because goats eat cabbages. How does he get everything across in the shortest number of trips? Now, I'm not going to go through this puzzle in much detail, but I just want to bring up what makes this a puzzle is the first time someone had used whimsy and fun to sweeten the pill, to make a mathematical puzzle, or it's really a logic puzzle, entertaining to do. So you're told this and you think, well, this is a fun situation. It's quite comic. You also want to know how it's done. In order to solve it, you don't actually need any technical expertise. And that's the other thing about what's the difference between a puzzle and a problem? I think all puzzles are problems, but not all problems are puzzles. For something to be a puzzle, it's got to require the minimum amount of technical expertise, so it's sort of anyone can do it. And all you need to know is simple logic. You need to work out, obviously, what is the thing that... There's only one thing that you can do. If you can't leave item A with B or B with C, you have to leave A with C. And then you work out how it progresses. But the other thing, which is the mark of a good puzzle, is that there is some kind of surprise. There is something that you're learning something, either about mathematics or about the world or about your own thought process. And what is interesting about this puzzle, it's so simple, is that you get this counterintuitive realization that you work out, that in order to get everything across, you need to take one thing across and then back and then across again, which feels completely counterintuitive, that aren't you kind of going backwards to do that. So that's something that's sort of really nice about this puzzle. And this puzzle, you talk about things that are going viral. This is probably the most viral puzzle of all time, even though obviously it was only spreading at the speed of horseback, because there is probably not one society, civilization in the world, apart from maybe a few in sort of the outback of Australia and the Amazon, that hasn't incorporated some version of this puzzle into into folk stories. And there are actually books written about all the different ways this puzzle has spread around the world. Now this is Alcuin, and it first appears in Alcuin. Another type of puzzle that Alcuin invented that I thought was quite fun, we could all do together, is the genre is called the kinship riddle. It's riddles about weird families. Okay, so this is from this Propositiones. And if two men marry each other's mothers, what is the relationship between their sons? Again, this is funny. You can't think about that without, I mean, it's funny because you think, what kind of family is that? That's never going to happen. But also, it can't be that difficult to solve. You don't need to know any maths, really. You only need to know what the relationship of people is within a family, what happens when you marry, what happens when you have a child. Yet try and do that in your head is really difficult. Your just head twists in and out, and it starts to be funny because you think, why can't I solve this simple thing? And so it sort of teases you a bit. So I thought, let's solve this. I think, personally, my favorite answer to this question is tense. But it's actually quite easy to solve when you start to write things down. And again, for most puzzles, you really need a pencil, an eraser, and the back of an envelope. So let's say, okay, two men marry each other's mothers. Let's call them A and B, Albert and Bernard. So we'll draw the family tree. Albert has married Bernard's mum. Obviously, Bernard's mum is the mum of Bernard, with Bernard's dad, who is invisible in the setting of the puzzle, but obviously must have existed. And Bernard marries Albert's mum. That's essentially what we get. Two men marry each other's mothers. We know that they have sons, so let's choose some nice medieval names. Steve and Trevor. That's essentially, once we put it like that, it's quite easy to see the answer. Steve and Trevor, we could have done it the other way around. They are both step-uncle or step-nephew, which we just say uncle or nephew. They're uncle or nephew to each other. So once you write it down, it's not that difficult, but it's quite fun, and the process of working it out is quite enjoyable. But once we have this interesting family, it's quite fun just to see, well, how far could we take it? Like, what else is going on here? So obviously, Albert's mum should be up there also, because Albert's mum is the mother of Albert. And then you see that Bernard has quite a peculiar relationship to Albert's mum, because as well as being married to her, she is also his grandmother. So that makes him grandfather or step-grandfather to himself. And you might have thought, well, that's kind of crazy. Surely there's never, ever been any time in the history of the world since Alcuin that this has ever been the case. And you would be wrong. And people of my age, anyway, will remember the Rolling Stones. And Bill Wyman actually was his own grandfather for a short while because he went out with a much younger girl, and it turned out that his son then married, I think, they were about to marry, and there was a big scandal. I'm not sure if they actually did or not. Mandy Smith's mother. So, truth is stranger than fiction. Okay, now we need to do some more Christmas stuff. This next question, I think, would be a really good question if there was such a thing as the Elf Academy, because obviously elves, I think they ride the reindeers around to try and deliver all the presents. So they've got to have a pretty good knowledge of geography. So I know this isn't the Geographical Institute, but why this is related to mathematics will become clear. Which is the furthest west of the following cities? Okay, might it be, we're going to do it by hands again, might it be Edinburgh? No. Good, class. How about Glasgow? Possibly. It's not good enough. We need hands up or not. Liverpool. Manchester. Or the capital of the West Country, Plymouth. Well, you are all wrong. And if I had asked this at the Mathematical Institute at the University of St Andrews, everyone would have got it right, because Glasgow is the furthest west. So why is this interesting? Everyone thinks that Plymouth should be west because everyone thinks that, or intuitively we see the British Isles as kind of north-south. Well, why do we do that, or what's the mathematics behind that? Obviously, the surface of the Earth is three-dimensional. It's a sphere. If we understood, and we were always looking at the sphere, we would know that England, the British Isles, is basically a diagonal poking west. But when you turn something from a three-dimensional space and you project it to make a two-dimensional representation, the map here, obviously you lose certain things, and one of the things that you lose is the sort of intuitive idea about how it all fits together. And I grew up after being born on, right here on the stage, I moved to Scotland, and one of the first things they teach you with incredible pride in Scotland is that the westernmost point of the British Isles is the Ardnamurchan Peninsula, which is round about there. So in Scotland, this is everyone knows this. So basically, that's why there are so many Scottish elves. So another Christmas question. Who knows what happened on December the 25th, 1642? It's a slight trick question. Yes? I like what you're thinking. Newton, correct. Newton was born. But the reason why it's a bit of a trick question, he was born on the 25th of December, but 100 or so years later, because that was in the Julian calendar, it was revised, and now we have the Gregorian calendar, so now he was born we say he was born on the 4th of January. But it's nice that he was born on Christmas Day, and that's a nice link to talking about the next person who I have sort of chosen to be important in the history of puzzles, which is this man, William Whiston. So William Whiston, little-known mathematician, but he was good friends with Newton, and Newton was the first Lucasian professor of maths at Cambridge, and Whiston was his successor. Whiston was also controversial. He only lasted 8 years because he was expelled from Cambridge for heresy. Now, so one of the things I like about talking about maths is that you get to talk about how maths affects lots of different things and how you can't really ring fence it into one subject, and somehow its influence is felt in other spheres. And when Newton came up with his laws of motion and the kind of the clockwork universe, how it all sort of fits together, it had a knock-on effect in people's understanding of religions. And so there was lots of kind of at the time of people sort of reconsidering their Christianity, holding on to Christianity, but having kind of different, interesting, and some say heretical views. And William Whiston was part of a kind of small kind of Christian sect who believed that the Holy Trinity was wrong, because Christ didn't have the same kind of value as the other two, and for not believing the Trinity, he was expelled. And he spent most of the rest of his life earning a living giving math lectures in the coffee houses of London and kind of arguing for his religious views. If you are to go on the Wikipedia page for him, what he tends to be most known for is that he really campaigned hard for the Board of Longitude to offer, which was set up by the government, to offer a prize for the person who could invent a machine or an implement that could work out longitude while at sea. And the reason why he was so keen for them to set this up and this prize money was because he thought he would be able to solve it and win the money, which he never did. But what is ironic or nice about that is that he is now remembered by people like me for coming up with probably the most famous maths puzzle about navigating the globe. Okay, and this also fits in with our Christmas theme. The question is, he was the first person to realize there's this really interesting, very simple but interesting mathematical sort of curiosity wrapped within this puzzle. A man walks around the circumference of the world. How much further does his head travel than his feet? Again, I love this type of puzzle because you look at it, you think that's a funny thing to say, to think about, and you want to know the answer. And your intuition, I hope, is probably quite different to what the answer is, so you get this nice surprise on the way. Well, the first thing I need to do, because obviously it's a Christmas lecture, what type of crazy man is going to want to walk around the circumference of the world? Thank you. Santa walks around the circumference of the world because, just say, there's noroviruses going around all his reindeer, and he has to walk to deliver all the presents. Okay, how much does his head travel than his feet? Let's think about it, and let's draw a sketch on the back of our envelope up here. Essentially, what I'm asking is this. We can assume, this is like a maths lecture, you can assume that someone can actually walk around the world. We are assuming that the world is a perfect sphere, so the circumference is like a grand circle, and we're going to say that it's exactly 40,000 kilometers. Right, so you're walking around, this is Santa here, he's going to walk all the way around. The distance that the head travels more than the feet is the circumference of that basically the dotted line minus the circumference of the Earth. The dotted line minus the circumference of the shaded circle. Now, you would have thought that this is 40,000 kilometers that he's walking around. The head is always, the feet are always, I'm going to say that Santa has the average height of a British adult male, 1.8 meters. The head is always 1.8 meters from the ground. So this up there, it's 1.8. He's going all the way around, and at the bottom, it's also 1.8 meters from it. You're going to think it's going to be, in the hundreds of miles, probably. It's going to be like a long. The head is traveling a lot longer. It feels like a lot longer. Anyway, let's work this out simply. We do need to know a little bit of technical knowledge, but I'm thinking that we should all know this, but just in case, revision notes. The circumference of a circle is 2 pi r. Okay, back we are. So, we've all got that. Well, what is the distance travelled by the feet? It's 2 pi r. What is the distance travelled by the head? It's 2 pi, and the radius is going to be h plus r, 2 pi r plus h. So that's 2 pi r plus 2 pi h. So the difference is going to be the bottom one minus the top one, which is 2 pi h. Okay, so let's work that out. It's 2 times pi, which is 3.14, or thereabouts, times 1.8, which is 11 meters. Okay, it's really not a lot. It's kind of wow. I mean, that's why, and William Whiston, there's basically one math textbook for 2,000 years, Euclid's Elements, and every new mathematician that came along did a new version with their kind of annotated notes and thoughts. And William Whiston came out with one when he was Lucasian Professor of Maths, and in it he said, isn't this interesting? Because when a man walks around the Earth, it's only like 11 meters, or it's only 2 pi h. But what's interesting isn't really that it's 11 meters. It's if you look at the answer, 2 pi h, nowhere does the answer include r, the radius of the Earth. In other words, it does not matter what sphere the man, Santa, walks around, the head is always travelling only 11 meters more than the feet. Okay, trivially, if you're walking around a dot, the feet don't walk anything at all, and the head walks 11 meters, that's 2 pi r. But also, just say you are walking around the moon, you're walking around Jupiter, you're walking around the largest sphere that it's possible to get in the universe, still, the head travels only 11 meters more than the feet, which is something which is surprising and interesting. So I prefer the puzzle set about a man walking around the Earth because that's how it was originally spotted by Whiston 350 years ago, but also because the way that it is normally stated, this puzzle, is as the rope around the Earth puzzle. The rope around the Earth puzzle, it might give you a bigger wow, but it's a lot more weird and bizarre and complicated to explain because you need to say there is a rope around the circumference of the Earth and it's taut. Then someone extends this rope by 1 meter. Extend the rope by 1 meter. Then what the person does is you need to pull up the rope above a circumference of the Earth so it's at the same height all around the Earth. And this is just where it gets complicated. Most people are like, why do you want to do that? So sometimes they say it's the iron bar around the Earth. That you have an iron bar around the Earth and you extend the iron bar by 1 meter and then you pull it up so that the iron bar is above the circumference at exactly the same. The question is, by extending something from 40,000 kilometers to 40,000.001 kilometers, i.e. tiny fraction, what animal can get underneath? And at first you would think, oh my God, just like nothing, I know an ant. But actually, there's a small dog. That small dog could get under. And I think by the time, if you've managed to follow all the stuff about this rope and then pulling it up, you would think, wow, that is surprising, because it would be also the case that if you had a rope around Jupiter or around the biggest possible thing, sphere in the entire universe, the exactly same thing would happen. Extend it by 1 meter, lift it up, you're going to get this dog underneath. So if I was asking that question, or I was being told that question, I would say, hang on a second. You've gone to all that work to get this rope going all the way around the Earth, and you're extending it by 1 meter with the purpose of trying to get animals to go underneath it. Why are you going to try and levitate it above that? Why don't you just pick it up at one point and pull that rope as high as you can? So that's also a really interesting question. What animal now can get underneath it? And this is something that it does depend on the size of the sphere, and you actually need A-level, if not beyond, trigonometry to work out. But it turns out that if you have this rope around the Earth, you extend it by 1 meter and you pull it, because I'm going to talk about festive animals, you can get about a pyramid of 100 reindeer will be able to go underneath it. It's basically 122 meters high, the height of Centre Point in London, which is, again, kind of counterintuitive. You're extending it only by a tiny amount, and you get so much slack. Now, quite often when I give my talks, I do maths and philosophy, so I'm not like that interested in applications. I'm interested in just like it's interesting. But quite often I say, well, why is that useful? How does that affect real life? Well, the fact that, we've been talking about circles, but it also works in straight lines. If you give something extend something a tiny amount, you get so much more slack than you would intuitively think. And this is why you get things like this happening. So when in the heat, if you have a rail track, you only need to extend that rail track by a really small amount, and the slack that you get actually creates really counterintuitively large bumps. Right, moving on to the next century, or maybe 2 centuries after that, in the Victorian times, and I'll talk about Lewis Carroll. So a great boom time for puzzles was the Victorian era, especially the late Victorian era, and one of the reasons for that was the growth in media and magazines and newspapers, and actually people realised that people wanted to read and do puzzles for pleasure. And Lewis Carroll, obviously, who's an Oxford Don, much more famous for Alice in Wonderland and Through the Looking Glass, but he also wrote several puzzle books. None of them were particularly successful because he wasn't good at writing a good puzzle. They were a lot more complicated, and they're a lot more too difficult really for them to be sort of general appeal. But he did invent a type of logic puzzle which has become a hugely popular type of logic puzzle, and actually really sort of useful and good applications, and pretty much any computer science course that you do, you will play around with puzzles like this. And it's puzzles where you have some people who tell the truth all the time, and some people who lie all the time. So puzzles involving truth tellers and liars. And Lewis Carroll was the first person, and it was only quite late in his life, in the 1890s, he scribbled around, and he worked out this precise puzzle, which he just did A, B, and C, but because this is a Christmas lecture, I've done it with different names. And this is his original puzzle. Dasher says that Dancer tells lies. Dancer says that Prancer tells lies. Prancer says that both Dasher and Dancer tells lies. Who is telling the truth? And in order to solve this, we're going to act this out. So I need 3 volunteers, 3 young volunteers. Yeah, you 3. Brilliant. Can you come up here? Yeah, 1, 2, 3. Is that okay? Well, one of you had your hand up. Was it you? Was it you? Well, whoever. So one of you is going to be Dasher, 1 is Dancer, and 1 is Prancer. Brilliant. So if you come and stand here, 3 in a row. Yes, if you look at sort of entrance exams and things to do computer science studies, that's full of questions about truth telling and lies. So we're going to get you, all 3 of you, in a row like this. So you, what's your name?
Catty.
Catty is Dasher.
Kaya.
Kaya is Dancer.
Alexandra.
And Alexandra is Prancer. So now I've forgotten your original names. I'm just knowing you as Dasher, Dancer, and Prancer. Okay, so how do you solve something like this? Well, what you need to do first, well, this is one way to solve it, is that you need to assume a truth value. You assume that someone is telling the truth, and then just like work it through and see what happens. So let's assume that Dasher is telling the truth. If you're telling the truth, then you're a liar, okay? If you're a liar, so that everyone knows you're a liar, this is the international symbol of being a liar, a Pinocchio nose. You put that on. You are now a liar. You're not a lawyer, that was Freudian, wasn't it? You are now a liar. You say that Prancer tells lies, but you're a liar, so actually you must tell the truth, okay? So you don't know nose for you. If you're telling the truth, if you say that both of you tell lies, well, you're not telling the truth. That's incorrect. So we have a system that is inconsistent. It doesn't work. So this is not a solution to the puzzle. So we can eliminate the possibility that you are telling the truth, unfortunately, Dasher. I think you might be liar. So if you're a liar, could you put on the symbol of lying? So Dasher is now lying. But you say that Dancer tells lies. But if you're a liar, that means that you tell the truth. We're in a system here that either you're a liar or a truth teller. There's nothing in between. So if you're telling the truth, you say that Prancer is a liar. So if you're a liar, we need to get one of these noses for you. You're a liar. You say that Dasher and Dancer tell lies, both which is not true. So you're actually, it's a consistent system. You're lying because that's not the case. You're saying that it's true, but it's not the case, so you're lying. So we have here a system that works the truth values, makes the system consistent, which means who is telling the truth? Only one of you is. Dancer! Thank you very much. A round of applause for our reindeer. Thank you. Okay, since we are on Pinocchio noses and lying, and Pinocchio, it's always on at Christmas time, tenuous link. I thought we would have some fun here about Pinocchio's nose. So we're all going to do this together. Pinocchio's nose is 5 centimeters long. Each time he tells a lie, his nose doubles in length. After he's told 9 lies, his nose will be roughly the same length as, who thinks it's a domino? Very good. A tennis racket, a snooker table, tennis court, a football pitch. Okay, well, let's just have a look. Well, let's go through the math, they say. So 9 lies, doubling each time, that's 2 to the 9, times 5 centimeters, the original length. Okay? You might be really good and be able to do 2, 4, like no one can remember that. If you learn one thing today, it's that 2 to the 10 is about 1,000. It's a really, really useful thing just to know, just for sort of making good estimates. 2 to the 10 is about 1,000. It's actually 1,024. So 2 to the 9 is going to be half that. It's about 500, 512. So 512 times 5 centimeters, which is obviously half a meter, 5 meters, or it is 5, which is 25 meters. So most of you are wrong. It is a tennis court. And also interesting, I'm a journalist, or maybe an ex-journalist. I don't do much journalism at the moment, but journalists are always trying to describe how big things are. And also, oh, it's the size of several football pitches. When it gets bigger, we say the size of several times the size of Wales. But the reason why I use a football pitch is football pitches, you think, well, there's stadiums, they've always got the 100-meter racetrack right next to them. So, rule of thumb, football pitches stadium, that's always going to be used that 100 meters, about 100 meters. So something which is a quarter the size of a football pitch is going to be a tennis court. Now that is the level 1 question. The level 2 question, neurons on the ready. If Pinocchio's nose is initially 1 inch, that's 2.54 centimeters long, it has a weight of 6 grams and is attached to a 4.18 kilogram wooden head, after how many fibs would it break and how long would it be?
What sort of wood?
Right, it is a good question. Mahogany. No, I don't know. Because the reason why I bring this up, the answer is apparently 13 fibs and 208 meters, because of this is the only thing in the entire lecture today which is actually the subject of a proper academic paper. This is what you study at the University of Leicester. Okay. At the end of the 19th century, there were 2 huge figures in puzzledom. Sam Lloyd in America and Henry Dewdney in the UK. And these 2 people, in a sense, I mean, Dewdney was a much more interesting mathematician, a fascinating man who was completely self-taught, and yet quite a lot of the maths that he found in his puzzles went on to be stuff that proper mathematicians still study to this day. Sam Lloyd, who's in America, became a lot more famous and a lot richer. He was very kind of American and entrepreneurial. And I want to use one of Sam Lloyd's puzzles because it's actually easier to do as a group. And it's called the Canals on Mars. It's from about 100 years ago. Okay, what we have, this is a picture of Mars. I want you to start at the letter T, and then you need to get your way through all of the canals and come back to T, saying a sentence in English. Okay? There is some sentence in English that you can say. Now, this is quite a famous puzzle and had a lot of attention at the time. And Sam Lloyd said that when the puzzle originally appeared in a magazine, more than 50,000 readers reported there's no possible way, yet it's a very simple puzzle. When the puzzle originally appeared in a magazine, more than 50,000 readers reported there is no possible way. Yet it's a very simple puzzle. Have you got the answer? Would you want to tell us what it is? There is no possible way. Okay, it is amazing how many people, the penny will not drop when you're literally saying to them again and again, there is no possible way. And what I like about this puzzle is that it really brings out the fact that sometimes when you start a problem, if you're looking in one direction, it's impossible to kind of go back from that direction and start in a new direction. That if you are totally focused in one way, even if someone is telling you the answer, it's hard to see it when it's right there in front of you. So as well as read the question, you need to sometimes kind of forget everything you know and then start again afresh. And often these puzzles are quite similar to magic tricks, that what magicians are sometimes trying to do is do something here but make you look over there, right? Sort of sleight of hand. And puzzles often, that is exactly the same thing. You want to lead the solver in one direction when the solution might be really obvious, but it's much more fun to try and distract them, take them go in a different way. And actually, there's a famous puzzle which is about the light bulb and the three switches. And this is a classic puzzle because it's set as a maths puzzle, but actually the answer is a kind of physics answer because it's all about that the bulb is going to heat up. But if you start trying to solve that puzzle, thinking about mathematical combinations, you're just not going to get it. You're just not going to get it because you're stuck in this way of thinking it's a maths puzzle. So sometimes you need to kind of go back. And once I was at a books festival and I was in the green room and I was chatting to Joe Nesbo, or Yule Nesbo, the Norwegian sort of best-selling crime writer. And he said, "Oh, you're a puzzles guy, tell me a puzzle." And I told him this puzzle. And he's the only person I've ever told that puzzle to who managed to solve it in front of me. And he basically said, "Okay, you're doing exactly what I do as a crime writer. You know, I'm writing all the characters in the first few pages, and obviously it's blindingly obvious who did it, who the murderer is. But all what I'm trying to do is to make the reader think it's not that person until right at the end. That's the pleasure of it." And he said, "Okay, so this puzzle, you're telling me it's a mathematical puzzle, but I know that's probably a trick. So what else could it be? What happens to bulbs?" And he basically reverse engineered it and solved it. And I thought that was very interesting to think that there is a kind of parallel with a great puzzle and also a fiction. So we're going to do some Christmas. How am I doing for time? Very good for time. If there is one mathematical sort of field, really, that Father Christmas, Santa Claus, has to tackle with every year, surely it is the traveling salesman problem, okay? Traveling salesman problem is you have all the different places that you need to go. You need to go to do a loop. You need to start where you are, go and visit all of them, come back to where you started in the quickest or shortest possible way. The first person to start thinking about this was Carl Menger in the 1930s, famous mathematician. But Carl Menger was actually, see what I did here, much more famous for something else, the Menger sponge. Okay, I don't know if anyone knows what Menger sponge is. Well, obviously some people here do. We've got some professors of mathematics. I'd be surprised if they don't know what it is. The Menger sponge, for those of you who don't know, is a really fun, fascinating object that's quite simple to describe and kind of cool to look at. Is that, let's say we have a cube. This is a cube. We're going to divide the cube into 27 smaller cubes, just like it's a Rubik's cube, say. So 3 by 3 by 3 by 3. So there are 27 cubes, and we're going to extract the middle cube in each of the sides, plus the very central cube. Okay, so there should be 27 if it's a block. Then we take out 7, so 6, 1 on each side. There are 6 sides, and 1 in the middle, that's 7. So we're left with something with 20 sort of cubelets like that. And then the next process is, let's treat it, it's a fractal object, so we're going to repeat the process, take each cube and do exactly the same thing. So we get this. You see, we've taken each cube, and within it we've made 27 smaller cubes, taken out the 7 centers, and we get this kind of hole, this sort of cube that's growing holes. And then we carry on one more iteration, and we get this. Okay, this is the Menger cube. We call this a level 3 Menger cube because we've done an iteration 3 times. And one of the reasons why this is a really interesting object is that each time we take out holes, we increase the surface area, but we reduce the volume. So in the limit, we're going to have an object which has no volume and an infinite surface area. which is kind of interesting. Okay, how is this relevant to Christmas? Well, we're going to get there. Sometimes I submit puzzles for Radio 4 Today programme. Now has a puzzle of the day at about 6:50 every morning. And there was one which I really liked, actually. I thought this was a really nice puzzle from, I think it was the University of Leeds set it. And so imagine you've got a cube. Just forget this for a while. You've got a cube and you hold it for a piece of string from one of the vertices, the edge, and then you dip it into water. When you dip it in halfway, what is the shape on the surface? And I think this is really interesting because it's really hard to visualize, even though it's a cube, like one of the most simple objects. It's really hard to visualize. Actually, what you get is a hexagon. I can show that here. It's basically, if you slice a cube like this, you get a hexagon. Okay, so you go halfway along each side and then do it diagonally. So you get two, that's, looks like it's Y fronts from here actually. But if you see it as the depth, you basically get, you split it, there's a way of doing a diagonal slice, which you get a hexagon, which is, so they're both equal sides, and you also get it when you're dipping the cube in. So the question is, what pattern do you get if you slice the mega sponge on one of those diagonal slices? Okay, and when I was asked this, I had no idea, but I was asked this by a guy called George Hart, who's a well-known American geometrical sculptor and geometer, and who's actually also the father of Vi Hart, who does these amazing YouTube doodle videos. And he said that this was probably the biggest wow that he knew of in mathematics. And this is a guy who's like, knows loads of wows. His business is wows of geometry, because he's there making these amazing sculptures, which is makes people feel wow. So it's not something that you might be able to work out for yourself. I certainly couldn't. But if you are to slice this level 3 mega sponge with a hexagonal slice, this is what you get. Which, as well as being surprising and wonderful, it's a fantastic image to end on, because it's basically like kind of a snowflake or a star at the top of a Christmas tree or in the sky. And it's almost exactly 6 o'clock, so thank you very much.